Hello, everyone. My name is Ming-Nan Cheng from Nuvoton Microprocessor Division. The topic to be presented today is the MCU security features for IoT security. I have divided my presentation into 4 parts. The first is the overview to IoT security. I will first introduce the hardware component of the IoT devices. Then introduce the data on these IoT devices and the importance of this data. Then extend to the role of IoT device security. Secondly, I will talk about the MCU security objectives. This session will first introduce the types of attacks that the MCU may face on IoT devices. Then describe the goal to be achieved by the MCU security functions. And then introduce the MCU security standards and the certification schemes. Thirdly, I will talk about the MCU security features. This section begins with an overview of the various security features of the MCU and the types of attacks that each security features can prevent. Then I will illustrate several security features to describe their design and use. These important security features include secure boot, unique identifier, trust zone, and the tamper-resistant module. Finally is the conclusions. I will conclude today's report with 2 notes. Let's begin by the IoT security overview. An IoT device basically consists of sensors, MCU, and actuators, and is connected to the internet through wire or wireless interfaces. The sensor is responsible for collecting surrounding environmental data, and then sending the data to the MCU. As the name suggests, the actuator is used to initiate specific actions. Switches controlled by actuators are often used on IoT devices to turn another device on or off. The MCU can be regarded as the brain of the IoT device. It is responsible for the operation and the transmission of data. The data of the MCU on the IoT device can be divided into 2 categories, general and the application specific. General data is loaded into the MCU before the IoT devices operate, such as the firmware, unique identifier, user password, encryption key, and etc. Application-specific data, including the command, passed from the MCU to the actuators, and the logs or status passed the cloud server. Another group of application-specific data, including commands, and the device status or logs. The value of IoT devices lies in the intelligence and the automation that results from the device execution. Taking a smart door lock as the example, after the fingerprint is captured by the sensor, the corresponding data is processed by the MCU and sent back to the cloud server for calculation. Once the result is returned, the MCU will send a command to the actuator to control the switch to open the door. This simple example illustrates how IoT devices collect and process data to facilitate everyday life. From this example, we can see that the data in an IoT device is its most valuable asset. This data asset is the object that MCU security needs to protect. The IoT system can be divided into 4 layers according to the hardware requirements, implemented functions, etc. From bottom to top, they are the device layer, network layer, cloud layer, and the application layer. Each layer has its own security targets that need to be achieved. At the device layer, data integrity must be guaranteed, and the secure communication is implemented at the network layer. Security authentication and the privacy protection are implemented at the cloud layer, and the trust applications are provided at the application layer. From the perspective of the overall IoT system architecture, the data integrity of IoT devices can be regarded to be the foundation for the security of the entire system. So the next question to consider is how to ensure that the data on the IoT device, or more precisely, the data on the MCU is correct and not tampered with. Let's start with the types of attacks the MCU may suffer from. Attacks against the MCU can be divided into software attacks, non-invasive hardware attacks, and the invasive hardware attacks. Software attacks exploit vulnerabilities in program code as a means of intrusion, such as Stack Overflow attacks. The non-invasive hardware attacks include side-channel attacks and fault injection attacks. Hackers create the encryption key through side-channel methods, such as differential power analysis. Hackers also inject faults like clock glitches and 40G glitches. These faults cause the microcontrollers to behave abnormally and leak internal data. Invasive hardware attacks operate in a way that destroys the MCU. Hackers first use chemical agents or physical means to remove the packaging on the chip. Then connect microprobes to wiring inside the MCU to read internal secrets or perform glitch attacks. Another example of an invasive hardware attack is to use the focused ion beam to modify the internal circuit of the MCU and turn off the MCU protection function. Most of the attacks encountered on IoT devices are software attacks, side-channel attacks, and fault injection attacks. Therefore, MCUs need to integrate appropriate security features to defend against these attacks to protect data. When choosing an MCU development platform, users usually start by evaluating datasheets or technical user manuals. However, it is difficult for general MCU users to judge whether the security features provided by the MCU are sufficient to protect data access just by reading documents. Fortunately, mature IoT MCU security standards and the certification schemes are already available. These standard and the certification schemes can help users, as well as MCU manufacturers, understand the potential security level of the MCU. I want to show you two common security standards. One is Platform Security Architecture. It is called PSA. And the other one is Security Evaluation Scheme for IoT platforms. It is called CSIP. PSA was originally a MCU security standard led by ARM. PSA defines the security requirement of the MCU platform, including protection profile, firmware application programming interfaces, and the hardware features. The certification scheme of PSA is divided into 3 security assurance levels. CCP is supported by global platform to certify the security of connected products, and its certification scheme can be divided into 3 assurance levels. The first 3 security levels are similar for both certification schemes. Level 2 indicates that the MCU is resistant to software attacks, while Level 3 indicates that the MCU is resistant to side-channel attacks and fault injection attacks. Next, I will describe the security features that an MCU should have to achieve a PSA for CCP Level 3 security level. The first is a secure boot. The security of the MCU is based on secure boot to ensure other security protection functions are properly activated. Additional security features required by the MCU include hardware isolation features, such as trust zone in the NPU. These features can be used to protect critical code and the data against software attacks. Cryptographic accelerators, true random number generator, and the key stores are used for data encryption and decryption, key exchange, and the digital signature verification. These hardware features are not only capable of defending against side-channel attacks, but also can be used to enhance the security of software protocols that implement secure communication, device authentication, and other functions. Temper pins and the temper sensors can be used to detect enclosure intrusion and defend against fault injection attacks. Unique identifier and the debug port management can be used in MCU product lifecycle management. In the next sessions, I will introduce the design and the function of several important security features in MCU. First security feature is the secure boot. There is an immutable ROM and a flash memory inside the MCU. A piece of boot code is stored in the ROM. It is called secure bootloader. Flash memory holds the application's firmware and its digital signature. After power on or reset, the MCU first executes the secure bootloader. The secure bootloader will use the preloaded firmware's public key to verify the digital signature of the firmware in flash memory. According to the digital signature algorithm, if the firmware content is not modified and assigned with the correct firmware's private key, the verification result should be correct, and the secure bootloader will jump to the firmware for execution. If the verification result is not correct, the secure bootloader will prevent the firmware from executing. Through the verification of digital signature, secure boot can guarantee the integrity and the authenticity of a firmware, so it can be said to be the hardware root of trust. Unique identifier. The meaning of unique identifier to MCU is equivalent to each person's unique fingerprint, which is used to identify each MCU individual. Since each MCU has a different unique identifier from others, unique identifiers are often used for device authentication. The unique identifier can also be used as a source for deriving encryption keys. Due to different sources, the encryption keys generated by each MCU will not be the same. The unique identifier was generated during production. The set of 96-bit or 128-bit numbers assigned according to the manufacturer parameters are used as the unique identifier for the MCU. Cryptographic algorithms are the foundation for MCU data security. Based on mathematical principles, cryptographic algorithms can help solve problems that are closely related to data security. The MCU usually integrates cryptographic accelerators to improve the performance of processing different algorithms. For example, symmetric key encryption (AES) for data encryption and decryption, hash function (SHA) for data integrity check, the digital signature algorithm (ECDSA) for digital signature generation and verification, and the key exchanging algorithm (ECDH) random number generator. These hardware accelerators are also designed with protections against side-channel attacks. Use hardware accelerators, allowing the processor to focus on handling application data transfers and the computations, thereby improving the execution efficiency of IoT devices. Trustroom is a trusted execution environment technology developed by Arm. On Cortex-M microcontrollers, the processor supports two execution states, secure and unsecure. When executing in secure state, we select the MCU is in the secure world. Conversely, when executing in non-secure state, the MCU is set to be in the normal world or non-secure world. Besides, other MCU resources, including SRAM, flash, and peripherals, are allocated to secure world and non-secure world through address mapping. Here is an example. The process can access all resources when executing in secure state. After executing the secure gateway instruction, the processor will switch to non-secure state. In this case, the processor can only access SRAM, flash, and the peripherals that are allocated to the non-secure world. Trustroom ensures that non-secure processors cannot access secure code and the data through the internal path. With this hardware isolation, the code and the data in the secure world will not be leaked or tampered with, even if non-secure code is compromised. The tamper-resistant module monitors the MCU surrounding environment at all times. It is used to detect abnormal events and trigger warning interrupts to notify the system software to prevent intrusion and tampering. Combined with the design of the printed circuit board, the tamper pins can be used to detect intrusion of the device enclosure. The tamper-resistant module also includes sensors to detect whether the working environment of the MCU is abnormal. For example, the input of the clock frequency is out of the normal range, or the input voltage has glitches. Once the tamper event is detected, the tamper-resistant module will generate a warning interrupt and trigger some adaptive actions, like clear backup SRAM or registers. Due to the capability to detect tamper events, the tamper-resistant module is helpful to detect fault injection attacks. In the previous introduction, we talked about the IoT system can be divided into 4 layers. From the perspective of IoT security architecture, the data generated by the underlying IoT devices will be transmitted to the upper layer for further use. Therefore, protecting the data integrity and the authenticity of IoT devices is the foundation of IoT security. To protect data on IoT devices, MCUs should have hardware security features to defend against software attacks, side-channel attacks, and the fault injection attacks. This is the end of my presentation. Thank you for listening.